In the wood-paneled chapel of the Catholic University of Louvain in Belgium, a priest lights a candle and kneels before a statue of Christ for his daily devotion. His name is Georges Lemaître, and it is 1927. As he rises, his eyes wander up to the towering windows that line the chapel's walls, and then out to the stars twinkling in the early evening light. He smiles, not in simple prayer, but in distant reflection, imagining the long, strange sequence of events that carried that starlight all the way to the Belgian sky. And here's what's so fascinating. Despite his faith, Lemaître's beliefs were missing a creator in the way you'd expect from someone in his position. He had no need for divine intervention when it came to the making of the universe, no 7-day miracle. Instead, he saw the cosmos as the natural consequence of natural laws, laws proven by mathematics and visible in the movements of the heavens themselves. That extraordinary insight would earn him 2 Nobel Prize nominations because Georges Lemaître was more than just a Catholic priest. He was also a theoretical physicist, a cosmologist, a man fascinated with the workings of what he might have called a perfect universe. And it was here, in Louvain, that he began working on a theory that would come to shape our modern understanding of the cosmos. It was all based on a remarkable observation that sounded almost absurd at first. Space itself seemed to be expanding, not the galaxies moving through space like ships on an ocean, but the ocean getting bigger. Mathematics had already laid out a possible history of the universe, and now Lemaître traces it backward in his mind's eye, like rewinding the greatest film ever made. He imagines a time before humans, before any living thing on Earth. Before that, of course, Earth must have formed as a barren, rocky ball orbiting a glowing sun. And before that, the sun itself ignited in a blaze of nuclear glory, crushed into being by the irresistible force of gravity inside a vast cloud of gas and dust. But even that cloud wasn't the beginning. That gas and dust was a consequence of many generations of stars living and dying before our own, igniting, fusing elements, and exploding in terrific supernovae that spread their elemental waste products across the cosmos. The atoms in your bones, the iron in your blood, the calcium in your teeth, those were once cooked in the hearts of stars that lived and died billions of years ago. Lemaître imagines a time before those many lineages of stars, before the chemical complexity we take for granted, when only hydrogen and helium floated inert in a lightless universe. And now, the key move. If space is expanding now, then in the reverse chronology of Lemaître's mind, it is contracting. There would be a point in this dark, gassy cosmos before the first star, when all the matter in the universe was compressed into a vastly smaller space. Atoms would become packed so tightly that even photons are unable to pass through. There are no light sources here, but it doesn't matter. The universe is utterly opaque. Light can't travel. Information can't spread. If you were somehow there, you wouldn't see darkness. You wouldn't see anything at all, because the concept of seeing depends on photons being able to move freely. In this contracting, reversed universe, everything is trapped. Then Lemaître pushes further back. When the universe crushes down even more, the atoms themselves are crushed, first into subatomic particles, and then into pure energy. In this small, dense universe, there is only radiation. Even Lemaître's imagination begins to falter here. The universe can become even smaller, even hotter. But what happens then? What happens at the limit? Lemaître pushes the unanswerable out of his mind, content in having grasped 13 billion or so years of cosmological history and unperturbed by the mysteries hidden in the first fraction of a second. But the theory he was unknowingly becoming the first true proponent of, the Big Bang Theory, would be debated, researched, and argued over for nearly 100 years. Because once you accept an expanding universe, the questions get louder, not quieter. How did the universe begin? What was the trigger for its incredible expansion? And could our simple matter brains ever even comprehend the real truth, even if we found it? Before Lemaître, studies of the cosmos had largely focused on our own place within it, its composition, its extent, its shape. But in the 13th century, one philosopher, Siger of Brabant, had dared to say something shocking, that the universe was eternal with no beginning. His view outraged theologians and earned him condemnation by the Pope in 1277. Rumor has it he was murdered with a pen,
an eerie symbol of the damage his ideas were believed to have done. Since then, no serious scholar had really contemplated changing cosmic history until Lemaître. His calculations rocked the cosmological world, but they weren't embraced by everyone. The claim was that the universe started its life a finite time ago in a single huge explosion, and that the present expansion is a relic of the violence of that explosion. To many minds, that sounded suspiciously like a modern scientific version of creation. And that's where the backlash really begins, because the universe wasn't just a scientific object, it was a philosophical battlefield. It was a cultural nerve, and Lemaître, quietly, had pressed his finger right into it. This Big Bang idea, some critics insisted, seems unsatisfactory, even before detailed examination showed that it leads to serious difficulties. One respected but controversial astronomer, Fred Hoyle, railed against Lemaître's expanding universe. He wasn't just skeptical, he was openly hostile. He even coined the term Big Bang as an insult, because the implication of an expanding universe is unavoidable. At some point, it must have begun expanding, and at some point the universe itself must have begun. Hoyle confidently declared that this was pseudoscience, little different from trying to justify the existence of a creator. In his view, the only reason we were so attracted to this novel theory was because the teachings of Genesis were so ingrained into our collective psyche that we couldn't help craving a cosmic beginning. And yet, Lemaître was perfectly happy to keep physics and religion separate. His mathematics didn't yearn for theological validation. He didn't need the Big Bang to prove anything spiritual. He simply followed the logic where it led. And crucially, the logic was not alone. It was supported by real observations of the real universe, made by an eminent astronomer just a few years later, Edwin Hubble. From the Mount Wilson Observatory northeast of Los Angeles, Hubble gazed tirelessly through the largest aperture telescope of the time, peering at some of the dimmest parts of the night sky. His measurements would prove conclusively the long-held suspicion that there were more galaxies than just our own Milky Way. That alone was mind-blowing. But then he found something nobody expected. To understand what Hubble saw, you have to remember something simple. Luminous objects like stars emit light as a result of fusion in their cores. The color and characteristics of that light depend on the temperature and composition of the star, yes, but they also depend on the star's movement. Just as an emergency vehicle's siren sounds different when it's moving toward you or away from you, light behaves in a similar way. In sound, the phenomenon is known as a Doppler shift. In light, it's redshift. The light waves emitted by stars moving away from us are stretched out. The same energy must now cover a greater distance, so the wavelength increases. And in the visible spectrum, longer wavelengths appear red to our eyes. So receding stars and galaxies appear more red than they actually are. Hubble wasn't the first to discover redshift in astronomical objects, but his observations at Mount Wilson uncovered a shocking truth. Every galaxy he studied was redshifted. Every single one was moving away. At first glance, this might support the old religious notion of Earth being the center of the universe, with everything fleeing from us like we're the cosmic bullseye. But the truth is stranger. Hubble saw that the more distant galaxies receded much more quickly than those close by. And that can only happen if the whole of space is expanding. Not galaxies racing through a fixed void, but the void itself stretching, like dots painted on a balloon moving apart as the balloon inflates. No dot is the center of the balloon's surface, but every dot sees the others receding. These observations were a striking vindication of Lemaître's mathematics and the concept of a tiny beginning to our universe. The equations weren't just elegant, they were describing reality. And then, decades later, another piece of evidence arrived almost by accident, in the most unromantic way imaginable: annoying noise. In 1964, researchers at Bell Labs in Holmdel, New Jersey, were using a gigantic horn antenna to tune into radio waves bounced off some of the early satellites. The work demanded absurd precision, and the scientists went to great lengths to eliminate all possible outside sources of interference. But despite their best efforts, their results were plagued by a persistent noise they couldn't eliminate.
At first, they suspected pigeons roosting in the shelter of the huge antenna, their droppings disturbing the signal. Then they wondered if it might be interference from bustling 1960s New York City some 50 kilometers away. But eventually, it became clear the noise wasn't pigeons or people. It was coming from outside our galaxy. It was a property of the universe itself. And today, we recognize it as cosmic microwave background radiation, the CMB. This radiation is a remnant of a time when the universe was very small and very, very hot, exactly as predicted by Lemaître's calculations. The expansion of space has since spread that radiation out, stretching the once intense heat waves into microwaves, leaving a background temperature of about 3 degrees above absolute zero. Those faint radiation scars burned into the fabric of space were a vindication of the Big Bang. And with that, the theory became the accepted model for the cosmos, a picture of expansion over some 13.8 billion years. But here's the thing, acceptance doesn't mean completion. There is still much work to be done, much understanding to be sought. The nature of the universe's first moments remains shrouded in mystery, and so many questions remain unanswered. What really was the Big Bang? And why does it break our understanding of the universe precisely where it matters most? Models of an expanding universe were originally based on Albert Einstein's theory of general relativity, which he formulated some 20 years earlier. But when Einstein heard about this radical new idea that the universe was expanding, he was uncomfortable. He famously declared that Lemaître's math was sound, but his physics was atrocious. The problem, again, was the implication. An expanding universe must have had a beginning. But this time it wasn't theology throwing stones, it was physics itself. The physics of the era had no explanation for how such a thing could happen, or even what it would look like. Lemaître extrapolated the universe back to what he described as the primeval atom, something that contained within it the potential for the entire immeasurable universe we see today. We can trace the beginning of time and space back to this single point. But as for what it looked like or how it worked, even now physicists aren't sure. When all the stuff of the universe is compressed into an increasingly smaller space, the laws of physics dictate that the density will increase, and so will the temperature. We have a decent idea of what happens to matter under extreme conditions thanks to experiments in gigantic particle accelerators. We can smash particles together, recreate tiny flashes of early universe energy, and learn how matter behaves at high temperatures. But experiments and understanding can only go so far. After that, things become unclear. Beyond the realm of particles, beyond subatomic quarks and their mysterious companions, is a compressed universe of pure energy, where weirdness rules. The fundamental laws of physics that govern everything we see and experience begin to break down. It becomes harder and harder to predict how this hyper-dense, hyper-hot primeval universe worked. How small could it really get? What makes it begin to expand? Over the last few decades, theoretical physicists have wrestled with tentative answers. One idea that reigned for a long time was that the cosmos began as a gravitational singularity, a single, one-dimensional point from which all of time and space were birthed. This is not dissimilar to the singularity at the center of black holes, like the one that lurks at the heart of our own galaxy. A singularity is a point so immeasurably dense that the gravitational pull reaches infinity. In a black hole, gravity is so strong that light cannot escape, but a singularity at the beginning of the universe would have no light to consume, because it already contained everything there was to contain. If the universe today is infinite in extent, then the infinitely small singularity would have a density and temperature extending to infinity as well. And concepts of infinity stretch our minds to the breaking point. But infinity is not the only problem. If, at the moment of its beginning, the cosmos had been an arbitrarily dense and hot point, many scientists believe the universe that resulted would have looked very different from the one we inhabit. There should be huge fluctuations in temperature and density from one end of the cosmos to another, but there aren't.
There should be ultra-high temperature relics left over from that infinite heat state, but there aren't. Space itself should be more lumpy, but it isn't. In fact, when looked at as a whole, the universe is remarkably uniform. The fluctuations we do see average out. You would struggle to pinpoint your location in the cosmos based on those features alone. Cosmologists go so far as to call the universe smooth, and the chances of a singularity producing a smooth universe are, in a sense, infinitely small.
So there is another option. It may have all begun with a period known as inflation. During this inflationary period, right at the earliest moments of the cosmos, space expanded exponentially, doubling in size from one moment to the next. Anything that grows exponentially gets big very fast. And this cosmic inflation was sufficient to put the bang into the Big Bang itself. It expanded far faster than the speed of light, not by objects breaking relativity, but by space itself stretching. It was enough to stretch the universe flat and make it uniform all over, which is precisely what we see today. According to the theory, the universe was imbued with energy that caused this exponential expansion. When the expansion ended, although we don't know why it ended, the energy inherent to the universe was converted into matter and radiation, marking the beginning of time and space as we understand it. The features of the modern universe only allow us to glimpse the final decillionth of a second of this inflation. That's 1 over 10 to the power 33, during which physics begins to make a little more sense. But we still don't know how long inflation lasted, and we don't know what started it. Could inflation itself have started with a singularity? Logic says no. If exponential expansion means doubling in size, then running it in reverse means the universe shrinks to half its size, then a quarter, an eighth, a 16th, and so on. The fractions become vanishingly small, but they never reach zero. From a purely mathematical perspective, a singularity of zero size is an impossibility. So right now, we don't have the tools to understand inflation any further back. We may never understand it. The origins of cosmic inflation extend back into the fog of pre-time, beyond the reach of science and into the realm of pure speculation. Thus, the Big Bang may not be the beginning of the universe at all, but rather the line drawn in cosmic sand marking the limits of our understanding. Not the start of everything, but the point where our story begins to make sense. And yet, if we really stretch our minds to the limit of what we can comprehend, the extreme edges of theoretical physics might give us tools to push through that fog. In 1981, in the shadow of St. Peter's Basilica in Vatican City, top cosmologists met for a conference organized by the Pontifical Academy of Sciences. Gone were the days when the Pope would issue condemnations of cosmological thinking. Or perhaps it is precisely because the favored Big Bang theories point toward a mysterious beginning that theological institutions now see an eerie parallel with their own questions. Regardless, at this conference among the hushed gardens of the Vatican, 39-year-old Stephen Hawking is an honored guest, and he presents some of his latest thinking on the beginning of the universe. He addresses the assembled scholars, his voice cutting through the last shreds of muttered conversation. His disability has already begun to take its toll, and a close friend sits alongside him, translating his words for others in the room. But while his speech may seem ill-formed, his thoughts have never been clearer, even if they sound like madness at first. The universe is finite, he says, but it has no edge. Someone standing at the far end of the observable cosmos, 13.8 billion light-years away, would see space exactly as we do. As you go back toward the beginning, space and time become fuzzy, but they curve around and cap off, much like the South Pole of our planet. Trying to understand what came before the universe is like asking what is south of the South Pole. The question itself is meaningless. Hawking's no-boundary proposal rocked the scientific community and left the rest of the world scratching their heads. We can understand that nothing is south of the South Pole, but imagining that idea applied to all of space and time is much harder. And yet, as we try to understand our place in the unfathomable cosmos, we can't help but grab at answers to potentially unanswerable questions.
What was there before? What is the universe expanding into? Why did it start at all? Testable science cannot yet give us the answers we seek. Time is a fundamental property of the universe in existence, so there was no time before the Big Bang. There was no before. Space is a fundamental property of the universe in existence, so there was no space before the Big Bang. There is no outside. The cosmos just is. Something that breaks all the laws of physics is impossible to visualize, let alone study. But even in the face of the truly mysterious, modern science isn't content to stop at "we don't know." Scientists continue to speculate, carefully. They take obscure properties of the universe or mathematical concepts and run with them, building theoretical possibilities that might, just might, give us a pinhole view into the impossible before and the intangible why. One of the most popular speculations is known as the Big Bounce, in which the universe is eternal but transitions between an expanding state described by the Big Bang and a contracting one known as the Big Crunch. The idea of a cosmos endlessly inflating and deflating has been around since the early 20th century, but only in the last decade or so have physicists developed ways it might be possible. The theory posits that in the earliest moments, reality is governed by quantum mechanics, and the strange properties of the quantum world mean that a contracting universe might be saved from complete collapse by quantum tunneling, jumping from just before the collapse to just after it, transitioning instantaneously from contraction to expansion. After a Big Bang-style expansion for billions of years, it's hypothesized that matter's gravity could eventually overcome whatever drives expansion and reverse it. But the latest observations suggest expansion is not slowing down as Hubble once expected, it's accelerating. That throws a wrench into the Big Crunch. So there is another option. In 2010, British theoretical physicist Roger Penrose presented conformal cyclic cosmology, built on some of the most complex mathematics in modern cosmology. It relies on conformal geometry, the geometry of shapes irrespective of scale. A chessboard has the same geometry no matter its size. Tiny in your pocket or gigantic on a lawn, the game remains the same. Penrose argues that the universe has moments where scale becomes meaningless. One is the murky high-energy instant just before the Big Bang, and the other is the far future when black holes have swallowed everything and energy is so low that space and time lose meaning. A tiny hot universe and a huge cold one seem opposite, but in conformal geometry they can be equivalent. So one may lead naturally into the other. We are living through one eon, and in a Google years or so, the death of this universe may lead to the birth of another. In both Big Bounce and conformal cyclic cosmology, our Big Bang is both a beginning and an end, one of many in an endless stream. But there is an even stranger theory born from strings. In spring 1995 at the University of Southern California in Los Angeles, the American theoretical physicist Edward Witten made an announcement that thrilled string theorists worldwide. String theory claims particles are ultimately one-dimensional strings, but different versions demanded additional higher-dimensional entities. The theory meant to unify physics had divided the community. Witten rejected the division, proposing that all versions might be true within an 11-dimensional reality, often framed as superstring or M theory. In this framework, our universe may be a brane in higher dimensional bulk, and the Big Bang could be triggered by the collision of higher-order branes. The energy released drives expansion, but tension could eventually cause retraction and collapse after 1 trillion years. This is often discussed as an ekpyrotic style model, echoing ancient myths of worlds born in fire. For now, we have no tools to detect those higher dimensions, so like the other theories, it remains informed speculation. The Big Bounce, conformal cycles, and brane cosmos ideas sit at the bleeding edge of modern cosmology. Like all good theories, they aim to make testable predictions, but so far no evidence has emerged to confirm any of them. Our understanding of the cosmos relies, like a house of cards,
on our evolving understanding of physics and mathematics. The true nature of the Big Bang and the meaning of the universe as a whole may always be incomprehensible to our monkey brains, or perhaps a new revelation will turn everything on its head tomorrow. For now, we can only keep asking and keep trying to see through the fog. You've been watching the entire history of the universe. Don't forget to like and subscribe, leave a comment to tell us what you think, and we'll see you next time.